Hello there. I'm so glad you're here, sharing this peaceful moment in the deep quiet of the night. Tonight, we're turning our gaze to one of the most brilliant stars we know, a massive, shimmering red giant hanging in the shoulder of Orion. For centuries, it's held its place in the sky, a quiet sentinel. But lately, this star has been whispering a secret. A dramatic change is coming, the kind that reshapes the cosmos itself. Imagine an enormous, ancient furnace running out of fuel. That's what's happening up there, miles beyond our counting. Tonight, we'll move gently toward that incredible moment, the grand finale of a giant star's life. We won't rush the science. Instead, we'll listen to the slow, deep story of stellar death and what it means for the light we see, even here on Earth. It's a vast idea, but we'll hold it softly, like a handful of cosmic dust. This channel is here to offer a little calm and curiosity at the end of a long day. If this gentle kind of wandering helps your mind settle or your thoughts grow soft, a quiet like and a soft subscribe help others find this same stillness. For now, let the darkness outside deepen, let the wonder grow, and we'll begin our quiet journey into the science of celestial endings. That great red star in Orion's shoulder has a name, Betelgeuse. It sounds almost playful when you say it quietly to yourself, but the thing it belongs to is anything but small or light. Betelgeuse is one of the most enormous stars you can see with your eyes alone. A true red supergiant, swollen and aging, burning through the last complicated stages of its life. If you were standing outside on a clear night, you could find it without much effort. First, you'd look for the familiar outline of Orion, that broad, confident figure many cultures have traced in the sky. Your eyes might be drawn to the 3 stars in a neat row that make up his belt. From there, you'd let your gaze drift upward and to one side, toward his left shoulder. That's where a softer, redder light waits. A star that doesn't shine icy white like many of its neighbors, but glows with a deeper, warmer hue, as if a coal has been held up against the darkness. If you linger on it, you might notice something else. It doesn't shine with a steady, sharp brilliance. It wavers, it flickers, and twinkles more than the stars around it. Earth's restless atmosphere certainly plays a role, bending and blurring the light as it reaches you. But Betelgeuse itself is also not perfectly calm. Its surface heaves and stirs, patches of hot and cooler gas rising and falling, making the brightness shift in a way that, if you could watch it over long stretches of time, would look almost like the star is breathing. For all its presence in our sky, Betelgeuse is far away. The light leaving it has to travel for about 700 years to reach your eyes. That means that the glow you see tonight began its journey long before you were born, long before anyone you know was born, long before the world around you looked the way it does now. You are looking at a message sent centuries ago from a distant, unstable surface, and only just now delivered to this one small patch of ground where you stand. Even at that distance, it's still one of the brightest stars in the night sky. Part of that is because it's intrinsically powerful, pouring out more energy than our sun could ever dream of. Part of it is because it's so huge. If you could somehow move Betelgeuse and place it where our sun sits, it would balloon outward to swallow not just Mercury, Venus, and Earth, but Mars as well, reaching almost as far as the belt of rocky fragments we call the asteroid belt. Everything you know, the orbit of our planet, the familiar path of the moon, would be entirely inside its outer layers. You and I, in that thought experiment, would simply be drifting within a star. It's a strange mixture to hold in mind. something unimaginably large and powerful that you can still reach with a single glance. A tiny dot overhead that, in reality, could contain the whole of our solar system within its bulk. The quiet red point on Orion's shoulder is the visible face of a giant nearing the end of its long, fiery life. Deep inside Betelgeuse, the story of that life has been written in layers. In its younger days, it was a main sequence star, living a simpler existence. Like our Sun, it once drew its strength from turning hydrogen, the lightest, most abundant element in the universe, into helium in its core. That process, nuclear fusion, is the engine of a star. At the temperatures and pressures inside, hydrogen nuclei are forced close enough together to fuse, releasing energy. That energy pushes outward as heat and light, creating an internal pressure that pushes back against gravity. Gravity, always patient and persistent, is trying to pull all the star's matter inward, to compress it into as small a space as possible. Fusion, in turn, is pushing out, trying to expand the star. For a long time, those two forces balance. The star shines steadily. It is, in a sense, in its long adulthood, quietly keeping itself in equilibrium. But the fuel at the center is not endless. Over millions of years, the hydrogen in the core is steadily used up and turned into helium. At first, the star can keep going by burning hydrogen in a shell around the core, but eventually, the very center is left rich in helium and poor in hydrogen. In a star as massive as Betelgeuse, that's when things begin to change more dramatically. Without enough hydrogen to keep the original fusion process going at the core, gravity starts to win again. The central region contracts, growing smaller and denser, and as it contracts, it heats up. In a star this heavy, that extra heat is not a small detail. It becomes enough to spark a new kind of fusion. Helium nuclei start to fuse into heavier elements. Like carbon, the engine restarts in a new mode. This pattern repeats. Each time the core exhausts one kind of fuel, gravity squeezes it tighter. Each time the temperature rises enough, a new, heavier element starts to fuse. Around the core, shells of different elements build up, hydrogen burning in one layer, helium in another, carbon and others farther in. The star's structure becomes like a set of nested rings, each one representing a chapter in its history, each one a different kind of fire. All the while, the outer parts of the star respond to the chaos within by swelling. The energy from these deeper, more intense reactions pushes out on the star's outer layers, making them puff up and cool down. That's why Betelgeuse, in this stage, appears as a red supergiant. Its surface temperature is cooler than many other stars, which shifts its color toward the red, but its sheer size more than compensates, keeping it brilliantly bright in our sky. There is, however, a kind of limit built into this process. As the star works its way through heavier and heavier elements, it eventually begins to build up iron in its core. Iron sits at an awkward point in nuclear physics. Fusing lighter elements into heavier ones, up to iron releases energy, which helps the star resist gravity. But iron itself does not give up energy if you try to fuse it further. It resists. At that point, the star has a problem. The usual trick of lighting a new fire in the center to push back against gravity no longer works. Once enough iron accumulates in the core, the balance that has held for so long can no longer be maintained. Fusion stops supporting the deepest part of the star. Gravity, which has been quietly waiting all along, finally has its way. The core begins to collapse in on itself, catastrophically fast on human timescales, and the outer layers suddenly unsupported, start to fall inward as well. The complicated details of what happens next involve shock waves and rebounding matter, but the broad picture is simple. The star blows itself apart in a supernova explosion, casting its outer layers into space and leaving behind a dense, exotic remnant at its heart. Betelgeuse is believed to be somewhere very near that final threshold. It has swelled into its supergiant phase. Its core is heavy and complex. The processes that will eventually end in a supernova are already in motion, even if they unfold over timescales that dwarf our own. When people say that Betelgeuse could explode at any moment, what they really mean is that, on the scale of a star's lifetime, this last stage is short. It might be tomorrow, or it might be tens of thousands of years from now. To a human, that gap is enormous. To a star that has burned for millions of years, it is a closing chapter. If you imagine that explosion from here on Earth, it's almost wonderfully unreal. Betelgeuse is far enough away that we are safe from the radiation and shock of its death. There will be no harmful waves sweeping over our planet, no sudden devastation. Instead, we will be offered a spectacle. For a few months, perhaps 2 or 3, that point in Orion's shoulder could flare until it rivals, or even outshines, the full moon. Nights would be transformed, an extra bright presence in the sky, casting gentle shadows, a new, temporary light that would be visible even against the daytime blue. People would step outside and look up not just at the moon, but at the ghost of a collapsing sun from hundreds of light years away. And then, slowly, it would fade. The fireworks would quiet. The thrown-off material would cool and thin, and the bright point we once called Betelgeuse would no longer be visible to the naked eye. Orion's familiar outline would remain, but that soft red shoulder would be gone, replaced eventually, and only in telescopes by a faint remnant where a giant once burned. Because of that, there's a bittersweetness in the knowledge that Betelgeuse hasn't exploded yet. The longer it waits, the longer we get to share a sky with it. Every clear night is another chance to see a star in the last long stretch of its life, still hanging there, still sending out its reddish glow. In recent years, Betelgeuse has been drawing extra attention. It has always been a variable star, one whose brightness changes over time, but a few changes were dramatic enough to catch not just scientists' instruments, but the notice of people all over the world. Around 2009, for example, careful measurements suggested that its apparent size on the sky, how big it looks when you resolve it with powerful telescopes, had shrunk by a noticeable amount, somewhere around 15%. That's not the kind of thing you see every day. It hinted at restless motions in its outer layers, at a star whose surface is far from still. Then, a decade later, another, even more striking event unfolded. In late 2019 and early 2020, Betelgeuse dimmed in a way no one had seen before. To the human eye, under a dark sky, it was clearly fainter than usual. To instruments, the change was stark. At its lowest point, the star's brightness had dropped to about 1/3 of its normal level. It was as if someone had reached up and turned down the dimmer switch on one of the sky's most familiar lights. People noticed, some wondered, or perhaps secretly hoped, that this was the sign, the last flicker before the grand collapse. News articles and conversations began to ask whether we were about to witness a once-in-a-lifetime supernova. The idea was hard to resist. Imagine being alive not just during the slow, steady life of Betelgeuse, but at the exact moment of its final flare. The thought alone was enough to stir a quiet excitement, even in those who knew the odds were small. astronomers turned some of their best tools toward the star, including the Hubble Space Telescope, which observes from above Earth's blurring atmosphere. Hubble had already been watching Betelgeuse, and in September of 2019, it recorded something interesting: a plume of hot material moving away from the star's surface. That material was part of the star's outer atmosphere, heated and then flung outward into space. Over the next few months, that outflow continued to evolve. It expanded and cooled as it moved away, just as a breath of warm air disperses and chills as it travels. By December, when observers on Earth saw that the southern half of Betelgeuse looked especially dim, a picture began to come together. The star itself was still burning, but some of the material it had thrown off appeared to have drifted into our line of sight. The leading idea is that this outflow contained elements such as carbon that, as they cooled, condensed into tiny solid grains, dust. On its own, each grain is almost nothing, a microscopic speck floating in space, but taken together, they form a thin, dark veil. From our vantage point, that veil passed in front of part of the star, blocking some of its light. Betelgeuse hadn't turned down its own brightness from within. It had, in a way, pulled a curtain halfway across its face. You don't have to picture a sharp-edged mask to understand it. Think of a thin cloud drifting in front of the Sunday. The sun's power hasn't really changed, but the world around you softens for a moment as some of the light is scattered and absorbed. With Betelgeuse, the cloud wasn't made of water droplets in Earth's sky, but of dust grains circling a distant star. When that cloud crossed our line of sight, we saw the star dim. When it moved on, or dispersed, the brightness returned. By around April 2020, that is exactly what seemed to have happened. Betelgeuse gradually climbed back to its usual brightness. The extraordinary dimming faded into memory, and careful measurements confirmed that the star's output had, for the most part, gone back to normal. There was no sudden blast, no daytime star, no final flash. Just a reminder that massive, aging stars can shrug off pieces of themselves, shaping their own surroundings with clouds of gas and dust long before the ultimate explosion arrives. For some, that may have felt like a story without the dramatic ending they had hoped for. No supernova, no spectacular light show. But in another sense, it was one more quiet piece of the puzzle, one more glimpse into the personality of this giant. Betelgeuse is not just a ticking bomb. It is a living, changing object, shedding material, pulsing, and shifting, interacting with its own environment in ways that can surprise even those who study such stars for a living. On a calm night, none of those details are required for you to stand under the open sky and simply look. You don't need to remember the exact distance, or the names of the elements in its core, or the dates when it dimmed. It's enough to know that the red star in Orion's shoulder is vast, old, and in the last long stages of its life. It's enough to let your eyes rest on that flickering point of light, to remember that what you see began its journey centuries ago, and that somewhere out there, beneath that glow, matter is being rearranged in ways that will, one day, end in a blaze. Until then, Betelgeuse keeps shining, sometimes a little more, sometimes a little less, a giant heart still beating in the darkness, and you, for a brief while, get to share a sky with it. And while Betelgeuse moves slowly toward its ending, elsewhere in that same sky, far beyond the red pulse in Orion's shoulder, there are places where stars are only just beginning. Hubble has spent years turning its patient eye toward those regions, sending back images that look almost like dreams, pillars, veils, tangled threads of light. When you look at those pictures, it can be hard to remember that you're not seeing paintings, but clouds of real gas and dust, lit and sculpted by newborn suns. One of those scenes shows something that looks like a tower, rising up from a hazy floor of light. Astronomers call it a pillar or a spire. Inside the Eagle Nebula, a vast stellar nursery where stars are forming from cold, collapsing clouds. In the image, the tower is dark against the glow behind it, its surface rough and knotted, like stone that has been carved by a very slow wind. It stretches higher than your mind quite knows what to do with, about 9.5 light years from base to tip. If you could travel along its length at the speed of light, it would still take you nearly a decade to reach the top. Despite its solid look in the picture, the spire isn't rock at all. It's made of gas and dust so thin that if you scooped a handful of it and brought it into a room on Earth, you'd call it a better vacuum than anything you could make in a lab. But in the emptiness of space, that gas is dense enough to hold together, dense enough to feel the pull of its own gravity. The darkness comes from how thick it is compared to the surroundings. It blocks the bright light behind, turning itself into a silhouette. All around it, just outside the frame of the image, lives a cluster of hot, young stars. They are bright and fierce, pouring out floods of ultraviolet light and streams of charged particles, stellar winds that rush outward in all directions. Those winds and rays beat against the spire like an unseen storm. The hazy glow that seems to hug its edges in the picture is hydrogen gas being heated and driven off, boiled away by the relentless ultraviolet light. The darker patches, where the structure looks almost black, mark places where the gas is denser and more resistant, holding together a little longer against the onslaught. This slow erosion does more than just sculpt beautiful shapes. As the hot, heated gas pushes and presses against the colder, denser pockets, it squeezes them. That extra pressure can help those pockets collapse under their own gravity. Inside them, the material draws inward, growing denser and hotter, until, someday, a new star ignites. In the image, you can see tiny bumps and knots along the spire's surface. They look like small irregularities, little nubs on a tower's edge. In reality, each one is roughly the size of our entire solar system, wide enough to contain the orbit of every planet you know. Within those knots, stars are already forming. Gas slowly falls inward, feeding the growing objects at the center. As long as there is material around them to draw in, they will continue to grow. If you could somehow sit quietly inside one of those dense cocoons, you would feel nothing on your skin, hear nothing with your ears, and yet all around you, atoms would be drifting inward, responding to gravity's call, building the heart of a future sun. The background glow in the picture comes from more distant gas, lit up by the same brilliant young stars. The colors you see, soft reds and cool blues, are a way of translating invisible kinds of light into something our eyes can understand. With hydrogen shining in reddish tones and oxygen glowing in blues and violets. From there, your imagination can drift farther out, past the Milky Way, to one of our small neighboring galaxies, the Small Magellanic Cloud. It hangs near our galaxy like a faint, misty companion, and within it lies another star-forming region Hubble has revealed in astonishing detail. In that image, called NGC 346, the light and darkness are even more tangled. Bright knots of newborn stars crowd together in the center, surrounded by torn-looking arches and filaments of darker gas, like soot smeared across a glowing canvas. At the heart of NGC 346 is a cluster of stars packed tightly together, pouring out light and energy. Around them, A ragged loop of cold gas curves like an uneven arch, partly enclosing the cluster. Once again, the radiation from the stars is striking that gas, heating its surface, stripping away material, and driving it backward, like sand blowing off the crest of a dune. In the Hubble picture, you can trace faint, wispy trails streaming away from small, dense clumps. Those are the wind tails, marks left behind as the harsher parts of the cloud are scoured away, while the tougher cores stubbornly remain. Within that cluster lies the brightest known star in the Small Magellanic Cloud, a beacon among beacons, helping to light the entire scene. Around it and its siblings, the same quiet process goes on as in the Eagle Nebula, gas being pushed, compressed, and sometimes forced into collapse, giving birth to yet more stars. From our point of view, it all seems frozen in an instant. But if you could speed up time, you would see the gas curl and erode, the dark knots shrink and glow, the shapes changing as new suns switch on, and old clouds are blown apart. Not every Hubble scene shows beginnings. Some reveal endings instead. One of the most famous is the Crab Nebula, a delicate, tangled cloud of filaments and wisps expanding into the darkness where a star once stood. Nearly 1,000 years ago, in the year 1054, people in China and Japan looked up and saw a new light bloom in the sky. It was so bright that, for a while, it could be seen even in the daytime. They didn't know it then, but what they were watching was a massive star tearing itself apart in a supernova. Today, when we look at that same patch of sky with Hubble, the star itself is gone. In its place is the glowing shell of material it threw off, still racing outward, still lit from within. The nebula is made mostly of gas that was once part of the star's outer layers, now stretched and twisted into filaments by magnetic fields and turbulent motions. There is hydrogen there, and heavier elements too, carbon, oxygen, and more cooked in the heart of the star and flung out into space to be recycled into future generations of suns and planets. Near the center of the image, almost easy to miss if you don't know where to look, lies what remains of the star's core, a neutron star. It is impossibly small compared to what came before, only about 30 kilometers across, yet more massive than our Sunday. In that tiny sphere, matter has been crushed so completely that atoms have been flattened, their components packed together into a dense, strange state. This remnant spins incredibly fast, turning about 30 times every second. With each rotation, it sweeps beams of high-energy radiation, including X-rays, out into space, like the twin beams of a cosmic lighthouse. When those beams happen to cross our line of sight, we see the neutron star as a pulsar, a source that seems to blink on and off with precise regularity. That steady flicker, invisible to your eyes but obvious to sensitive instruments, is part of what powers the pale blue glow spread through the Crab Nebula. The dead star's rapid spin and intense magnetic field continue to pump energy into the surrounding gas, keeping it lit long after the original explosion has faded from human memory. In this way, even in death, the star continues to shape and illuminate its neighborhood. If you let your thoughts drift back closer to home, to the familiar constellation of Orion, you find another Hubble image crowded with stories. Not far from the red shoulder where Betelgeuse hangs, there is a patch of sky that to the unaided eye looks like a small, fuzzy smudge in Orion's sword. Through Hubble's gaze, that smudge becomes the Orion Nebula, a rich tapestry of color and structure, and one of the closest star-forming regions to Earth, only about 1,300 light-years away. In the picture, The Orion Nebula spills across the frame in soft folds of pink, purple, and gold. At its center, in a bright, almost overexposed patch, 4 stars stand out, arranged in a tilted quadrilateral. Together, they are known as the trapezium, and they are some of the most massive stars in the region. Their combined light and heat flood the surrounding gas, carving out a cavity and setting the whole nebula aglow. Around them, scattered in the haze, are thousands of other stars, about 3,000 in all, some of which were first recognized clearly only thanks to images like this. Many of those stars are extremely young, still wrapped in the remnants of the disks they were born from. In the Hubble image, you can see some of those disks as dark, flattened shapes silhouetted against the bright background, or as small, glowing ovals with darker centers. These are protoplanetary disks, swirling rings of gas and dust that, given enough time, may clump together into planets, moons, and smaller bodies. Somewhere in that crowd, there may be future systems not unlike our own, worlds quietly assembling grain by grain in the dim light of their infant suns. At the upper left of the Orion Nebula image, one star shines in a way that makes the surrounding dust stand out, turning that local patch into a smaller, separate region called M43. Elsewhere, you can trace sharp, curved lines where denser gas stands firm against the relentless ultraviolet light from the biggest stars. At the edges of some of those arcs, you see shapes that look like the leading edge of a wave, or the curved ripple in front of a boat moving across water. These are bow shocks, formed where a star's motion and its own outflow collide with the stronger wind and radiation streaming from its larger neighbors. On one side of the nebula, a wall of gas marks the boundary of the cavity, hollowed out by the trapezium's energy, a kind of inner cliff, where bright, ionized gas meets darker, cooler material beyond. If you look closely at the dimmer parts of the image, scattered through the glowing background, you can find tiny red points, almost lost among the brighter stars. These faint embers are brown dwarfs, objects too small to sustain the steady nuclear fusion that keeps stars shining, yet too large to be called planets. They are sometimes nicknamed failed stars, though there is something quietly dignified about them, bodies that lit up briefly and then settled into a long, cool existence. Together, these images, from the towering spire in the Eagle Nebula to the tangled cluster in NGC 346, to the ghostly crab, to the soft light of Orion, show different moments in the life of starlight. In some, stars are being born, carved out of cold, indifferent clouds by gravity and pressure and radiation. In others, a star has already lived its bright life and come undone, leaving behind a glowing shell and a tiny, furious heart. All of them are distant, silent, and yet, through the patient work of a telescope orbiting far above our atmosphere, they have become part of the night you carry in your mind. You don't need to remember the catalog numbers or the chemical names to let them rest with you. It's enough to imagine that, while you lie here breathing slowly, there are pillars of invisible wind, sculpting towers of gas, clusters of newborn suns, lighting up jagged arches, shattered stars still stirring the clouds they left behind, and dusty cradles where future planets are gathering themselves in rings. Somewhere out there, within the same universe that holds your small, quiet room, all of these scenes are unfolding at once, at their own unhurried pace. And if you let your thoughts drift even farther than those nurseries of gas and dust, you begin to reach scales where even whole star-forming clouds feel small. Past the places where single stars are born and die, the view widens into the realm of galaxies great, spinning cities of starlight, each one holding hundreds of billions of suns, their stories woven together over billions of years. One of those cities is known as the Pinwheel Galaxy, or M101. In Hubble's images, it looks almost gentle, a wide, pale disk hanging in the dark, its spiral arms unfurling like slow-moving waves. From edge to edge, it stretches across space in a vast, delicate swirl. It is what astronomers call a grand design spiral galaxy, meaning its arms are clearly drawn and easy to trace, rather than faint or broken. You can follow them from the bright central region all the way out to the dimmer, more scattered outskirts, as if you were tracing the curve of a shell with your fingertip. The pinwheel is not some unimaginably distant stranger. It's a kind of near neighbor in cosmic terms, about 21 million light-years away, and roughly similar in size to our own Milky Way. When you look at its picture, you are seeing another galaxy that could, in many ways, be a cousin to the one you live in, another great whirlpool of stars suspended in the dark. Along its arms, patches of stronger color stand out, soft pinks and blues and whites clustered together, like beads on a string. Those are places where stars are being born in large numbers. The gas there is dense enough to collapse into new suns, and the light from those young, hot stars, in turn, lights up the gas around them. The pinwheel has an unusually high fraction of these glowing star-forming regions compared to some other spiral galaxies. In simple terms, it is busy. It is an active galaxy, full of stellar birth and the echoes of stellar death. Part of that activity is driven by violence. When massive stars reach the end of their lives, they explode as supernovae, sending shock waves through the surrounding gas. Those waves can compress nearby clouds, nudging them toward collapse, and eventually toward forming new stars. Superheated gas, stirred up by these explosions, glows fiercely and helps mark where the action is. Deep in the galaxy's core, material spirals in toward a central black hole. As it falls, it heats up and radiates energy before crossing the point of no return. Even if you can't see the black hole itself, you can see the influence of all this infalling matter. The result is a galaxy where creation and destruction are tightly linked, each feeding the other in a slow, ongoing cycle. If you move your attention to a different corner of the sky, Hubble shows you another galaxy with a very different personality. It's long and narrow in the image, like a glowing ember or a stick of incense, and because of that, people call it the Cigar Galaxy, or M82. Threaded through its core are streaks of deep red, flaring outward above and below the central disk, like flames or fountains. Those red plumes are hydrogen gas, heated and driven outward in vast outflows, wind on a galactic scale. The Cigar Galaxy is what astronomers call a starburst galaxy. That means it is forming stars at an unusually high rate, burning through its available gas in a burst of activity. In M82, new stars are being born about 10 times faster than in the Milky Way. If you imagine our galaxy quietly brewing stars in a long, steady simmer, M82 is more like a pot that has just come to a rolling boil. This frenzy is not happening in isolation. Nearby, in space, sits another large galaxy, M81, so close that in cosmic terms the two are almost brushing shoulders, only about 300,000 light-years apart. Their mutual gravity tugs on each other, stretching and distorting their disks. Much like how the moon's gravity pulls on Earth's oceans and raises tides, these galactic tides pull on gas and stars, dragging them into new patterns, funneling clouds into some regions and away from others. In M82, These gravitational interactions have helped channel gas inward, packing it into the central regions where it can collapse rapidly and form clusters of massive, short-lived stars. Those stars pour out strong winds and radiation, and when they explode, they add even more energy to their surroundings, blowing gas out of the galaxy's plane in those great red plumes. It is a feedback loop. Close companionship with M81 stirs the gas. Stirred gas forms more stars, and those stars in turn reshape the galaxy again. Deep within M82, there are also compact, extremely bright sources of X-rays. In some of Hubble's and other telescopes' views, they appear as vivid pinkish dots. One of them, often called M82X2, shines with about 100 times more X-ray radiation than an object of its type and mass was expected to produce. Its light suggests that matter is falling toward something very dense, perhaps a neutron star, or a small black hole at a rate and in a way that stretches our usual models. Nearby, another bright source, M82X1, is believed to be a black hole, yet it emits less X-ray light. The details are complex, but the feeling is simple. Even in galaxies we thought we understood, there are still points of mystery, small regions that behave more intensely than our predictions say they should. Not all of Hubble's views of galaxies show starbursts at their peak. Some reveal the quieter, lingering aftermath of a single star's death inside a larger stellar city. In our own Milky Way, one of the most striking of these remnants is called Cassiopeia A. In images, it looks like a broken ring of colorful knots and filaments, a bubble of debris that has been shattered and twisted. It lies about 11,000 light-years away, close enough, in galactic terms, to feel almost like it belongs to our immediate neighborhood. Cassiopeia A is the youngest known remnant of a supernova explosion in the Milky Way. The light that first reached Earth from that explosion would have arrived only a few hundred years ago, roughly 3 centuries in the past. Strangely, there is no clear, widely agreed-upon record from that time of anyone seeing a brilliant new star appear in that part of the sky, as happened with some other historic supernovae. One possibility is that the star had already shed some of its outer layers before the final blast, and that material may have muffled or absorbed much of the light, hiding the full brightness from view. Or perhaps it was simply overlooked, its brief flare lost among weather and war and the limits of human noticing. No one is quite sure. What we do know is that the shell of debris it left behind is still incredibly hot, tens of millions of degrees, and still racing outward into space at thousands of kilometers per second, on the order of 6,000 kilometers every second that passes. Over the centuries, this expanding cloud has grown to span about 10 light-years from side to side. Even now, the shock front continues to plow into the surrounding interstellar medium, compressing and heating the gas it meets. In Hubble's view, different colors trace different elements and temperatures, each filament a twisted piece of the star's former self, still moving, still cooling, still telling the story of a sudden, violent end. Farther along the Milky Way's plane, there is another cloud rich with color and structure, nicknamed the Lobster Nebula. The name comes from its shape in wider field images, where certain arches and protrusions suggest the outline of a crustacean's claws and body. It lies, like Cassiopeia A, roughly 11,000 light-years from us. But instead of showing the remains of one dead star, it is full of stars, just beginning their lives. Within the Lobster Nebula, Hubble reveals many protostars, young suns still wrapped in the material that formed them. They often appear as bright points, partly hidden by small, dark disks or cocoons of gas and dust. Those shadows are the remnants of the larger cloud from which they condensed, now falling inward or being shaped into flattened, rotating structures. In time, these disks may thin out, leaving behind planets and smaller bodies. For now, they serve as blankets, shielding the growing stars and obscuring them from clear view. At the heart of this region is a cluster known as Pismis 24, a gathering of especially massive and luminous stars. For a while, one object in this cluster, called Pismis 24-1, was thought to be the single most massive star on record, with a mass estimated at around 300 times that of our Sunday. Later, sharper observations showed that this one star was actually a closely packed system of at least 3 stars, each still around 100 solar masses. Even after this revision, they remain some of the heaviest stars we know about short-lived giants that pour energy into their surroundings and will someday end in powerful explosions of their own. Stars like these live fast and intensely. Their gravity pulls in material quickly. Their cores reach the conditions for fusion easily. Their radiation and winds blow cavities in the clouds that birthed them. Around Pismis 24, you can see those effects etched into the gas. Bright regions where ultraviolet light is stripping electrons from atoms. Darker towers where denser clumps are still holding out. It is a scene of both nurture and erosion, a place where the presence of a few massive stars reshapes the entire neighborhood. If you look beyond our galaxy again, to the small Magellanic Cloud we visited earlier, another Hubble image shows a different kind of beauty. The region called NGC 602 glows in shades of blue and orange, with ragged walls of dust and gas enclosing a central cluster of bright young stars. What makes this picture especially striking is not only the nebula itself, but what appears behind it. In the darker gaps between the nearby structures, countless distant galaxies fill the background. Tiny whirlpools and smudges of light sprinkled across the image. NGC 602 is located away from the crowded central parts of the small Magellanic Cloud. Because there are fewer foreground stars in the way, our view looks deeper into the universe, with less clutter. That relative emptiness acts like a clear window, allowing the background galaxies to show through. It also makes the local nebula easier to study. The shapes of its dust walls, the distribution of its gas, the positions of its young stars are not as hidden behind layers of other objects. In the center of NGC 602, a cluster of hot, newborn stars shines fiercely. Their light presses against the surrounding dust walls, eating away at their edges, carving out cavities much like those seen in the Eagle and Orion regions. You can trace the places where their energy has broken through, the frayed edges where darkness gives way to a soft, illuminated glow. It is another nursery, another place where gravity gathered gas into stars, and where those stars are now eroding the very clouds that made them, revealing themselves and opening their surroundings to space. Farther still, at distances that make even the pinwheel galaxy seem nearby, Hubble has turned its gaze to more distant spirals. One of them, known as NGC 1672, is a barred spiral galaxy, 60 million light-years away. In the image, a straight, bright bar of stars cuts across the center, and from the ends of that bar, sweeping spiral arms curve outward into the darker disk. 2 of those arms stand out clearly, decorated with knots of star formation. 2 others are subtler, tucked within the inner parts of the galaxy, less sharply defined but still there, winding around the core. In many spiral galaxies, the arms seem to flow right into the central bulge, connecting directly to the bright nucleus. In barred spirals like NGC 1000, 672, the pattern is different. The arms appear to begin at the tips of the bar, as if they are being launched from the ends of a rotating beam of stars and gas. The bar itself is not just an ornament, it plays an active role in the galaxy's life. Its gravitational pull helps funnel gas from the outer regions inward along its length, like a conveyor belt, slowly bringing material toward the center. Around this bar, NGC 1672 is experiencing a kind of starburst in miniature, an enhanced number of star-forming regions clustered in and near the bar and the core. As gas piles up there, it becomes more likely to collapse into new stars. Some of that gas may also find its way all the way into the very center, feeding whatever black hole resides at the galaxy's heart. We can't see that central black hole directly in these images. It does not shine on its own, but we can see the structures that guide matter toward it, and the knots of light that mark where that matter has paused on its way, becoming stars first. When you think of black holes, it can be tempting to imagine them as things, as dark spheres lurking in space. The reality is subtler, and in a way, stranger. A black hole is not a solid object in the usual sense, but a region where the fabric of space and time has been warped so strongly that there is a boundary from which nothing, not even light, can escape. Around that boundary, near and far, the rules of motion and time stretch and twist in ways that are hard to picture. Clocks run differently, paths of light bend. Matter falling inward heats, glows, and sometimes jets out in narrow beams before crossing the edge. For a long time, these ideas lived mainly in equations, quiet lines of math describing what should happen if gravity becomes that intense. Now, with telescopes like Hubble and many others, we see more and more hints that the universe really does behave this way. We see stars whipping around invisible centers, galaxies whose cores shine with the energy of infalling gas, ripples in space-time from collisions far away. The details can be as dizzying as they are beautiful, but for tonight, it's enough to know that at the hearts of some of those graceful spirals and quiet nebulae, the fabric of reality itself is curved into shapes that tug on everything nearby, and that we are slowly, carefully learning to read what that means. And in the quiet distances between those great swirls of starlight, there are places where even the brightest suns disappear. After wandering among galaxies, those wide, spinning cities, you eventually drift towards something stranger, something darker, something that refuses to shine. And yet, to understand how these shadows come to be, you have to begin not with darkness at all, but with overwhelming light. Every black hole starts its story as a star. Not just any star, but one born with a weight that almost dooms it from the beginning. These stars live under a kind of tension that never lets up, a delicate balance between two immense forces. Gravity, steady and insistent, pulls their mass inward, trying to draw every atom toward the center. Countering it is the heat and light created in the core energy released when hydrogen atoms are pressed so tightly together that they merge into helium. Each fusion of hydrogen into helium frees a little bit of leftover energy, just enough to push outward against the pull of gravity. In this balance, the star finds its long moment of stability. For millions of years, the outward pressure of light and heat holds gravity at bay. From far away, the star seems calm, a steady spark in a dark sky. But deep inside, this tug of war is what keeps it alive. Over time, though, the fuel that feeds that outward push begins to thin. Hydrogen becomes scarcer in the core, replaced by helium, which waits for temperatures even higher than before to ignite. If the star is massive enough, gravity provides that extra squeeze, heating the core until helium begins to fuse into heavier elements: carbon, oxygen, neon, silicon. Each of these stages lasts only a fraction of the time that hydrogen fusion did, and with every new step upward in atomic weight, the core grows hotter, denser, and more unstable. Imagine a sequence of inner rooms, each one smaller, more cramped, and hotter than the last. The star burns through its layers like a traveler moving inward, door by glowing door, each chamber offering less time and less energy to support the vast weight pressing down from above. Eventually, the core reaches iron, and iron is different. When lighter elements fuse into heavier ones, the process releases energy the star can use to push back against collapse. But fusing iron does not release energy, it demands it. No matter how tightly gravity crushes the atoms, iron will not help the star hold itself up. It simply accumulates at the center like a weight that cannot be lifted. Once enough iron builds up in the core, the balance that has lasted for millions of years begins to falter. Gravity gains the upper hand. There is no new fire to light, no new outward pressure to summon. The star's core starts to collapse, and the collapse is astonishingly fast. In less than a second, the center caves inward, squeezing matter to densities far beyond anything we can replicate on Earth. The outer layers, suddenly unsupported, fall inward too, racing toward the collapsing heart. When all that infalling mass slams into the core, now compressed to something unimaginably dense, the inner regions push back in a violent rebound. A shockwave bursts outward, tearing through the layers of the star, throwing them into space with indescribable force. That moment, that outward blast, is what we call a supernova. It is one of the most powerful events the universe allows, bright enough to outshine entire galaxies for a short time, hot enough to forge elements heavier than iron, cobalt, gold, uranium, and many others that later become part of planets, oceans, bones, and breath. What remains after this explosion depends on how massive the original star was. If the star was only moderately heavy, still far larger than our Sun, but not among the true giants, the collapsed core becomes a neutron star, a sphere only a few dozen kilometers wide, no bigger than a city, yet containing more mass than the Sun itself. Inside that small volume, matter is compressed so tightly that atoms no longer retain their structure. Electrons and protons merge into neutrons, forming a kind of ultra-dense ocean where the usual rules of matter barely apply. A teaspoon of that material, brought magically to Earth, would weigh more than mountains. You can imagine such an object as something incredibly compact, tiny, hot, spinning rapidly, still holding the memory of the star that once surrounded it. Even in its condensed state, it can radiate energy, pulse with beams of light, or distort the space nearby with its enormous gravity. A neutron star is a leftover, yes, but a lively one, still humming with the last vibrations of its violent birth. But if the star was heavier still, massive enough to push the collapse beyond even the strange state of a neutron star, another ending is possible. In those cases, the inward crush of gravity does not stop at the neutron stage. Nothing in the physics we understand is strong enough to resist further collapse. Matter continues to squeeze inward. Densities climb past the limits of known structure, and the equations that describe space and time warp into shapes far outside our everyday experience. What forms then is not a surface, Not an object in the usual sense, but a region, a place in space-time where gravity has folded itself so deeply that there is a boundary from which nothing can return. We call that boundary the event horizon. It is not a wall, not a surface that can be touched. It is the tipping point at which every possible path leads inward. Even light, racing as fast as anything cannot find a route back out once that horizon is crossed. Black holes come in many sizes, but all of them share this same nature. The smallest known ones weigh only a few times as much as our Sun, perhaps 4 solar masses or so. Yet their event horizons are tiny, just kilometers across. If you approached such a black hole from afar, you might not see anything at all until you were very close, because unlike stars, they emit no light of their own. What you would see instead is the behavior of everything around them. Gas spiraling inward, stretching into luminous streams, heating to millions of degrees as friction and gravity pull it ever closer. On the other end of the scale are black holes so enormous that they challenge the imagination. Some weigh billions of solar masses, and they formed surprisingly early in the universe's history, when the first galaxies were gathering themselves together. Their event horizons can span distances larger than the orbit of Neptune, or even engulf the entire span of our solar system. If such a black hole were placed where our Sun is, every planet, every moon, every icy rock and drifting dust grain would lie well within the boundary where light cannot escape. And yet, from far away, these giants would still be invisible unless gas or stars wandered too close and began to fall inward. Their presence is known by their effects, the way they sculpt the motion of stars near the center of galaxies, the way they ignite magnetized whirlpools of matter that blaze with radiation as they feed. Still, no matter how immense or how small, every black hole begins with the same quiet truth. Somewhere, in the heart of a dying star, gravity won. The tug inward grew stronger than the push outward, and the star's own light could no longer hold back the collapse. That inward fall, that irreversible bowing of space-time, is what remains. You don't need to remember the exact temperatures, or the sequence of fusion stages, or the detailed structure of the event horizon. It's enough to understand the shape of the story. A bright beginning, a long balancing act, a sudden collapse, and then a kind of silence so deep that not even light can leave it. While you lie here listening, somewhere far beyond the reach of any telescope you've ever looked through, more stars are living out that same arc. Some are still peacefully fusing hydrogen into helium. Others are already gathering heavy elements in their cores, inching closer to the moment when iron will tip the scales. And a few, in distant corners of the universe, are collapsing in this very instant, vanishing behind horizons that no one will ever see directly, leaving behind only the faintest influences on the worlds around them. In that sense, black holes are not just endings. They are reminders of the enormous forces that shape stars, galaxies, and the fabric of the universe itself. They are the shadows cast by gravity at its most intense, silent markers of where matter once burned fiercely enough to light up the darkness. And even though they cannot be seen, their presence threads through the cosmos like a quiet, unseen current, something ancient, patient, and endlessly deep. When you picture a black hole, you might see that familiar image in your mind. A dark circle surrounded by a glowing ring, like an eye made of fire and shadow. It's a powerful picture, but that black center you see is not really the black hole itself. It's more like the hole a missing piece makes in a sheet of light, the shadow of something you can't directly see. Deep inside that darkness, our equations say there should be something even more extreme than a neutron star. Neutron stars already stretch our imagination. Matter squeezed so tightly that atoms are crushed and their pieces packed together. A black hole, if we follow the math all the way in, seems to go further still. At the very center, the calculations suggest a point where density becomes infinite and size drops to almost nothing. That hypothetical point is called a singularity. But it's important to whisper another truth alongside that one. We don't actually know what is really there. The singularity is what happens when we push our current understanding of gravity and matter to its limits and beyond. The numbers stop behaving in sensible ways. Instead of giving us a clear picture, they give us infinities, a sign that our theories are being asked questions they aren't yet built to answer. Somewhere inside a black hole, the physics we know how to use may simply no longer be enough. There may be a new kind of behavior, a new description of space, time, and matter waiting to be discovered. For now, that inner region remains hidden from us, not only in practice, but in principle. The reason it stays hidden has to do with a boundary that wraps around the singularity, the event horizon. To understand why that boundary is so important, it helps to walk slowly back through the ideas of gravity themselves. For a long time, we've known that objects with mass attract one another. Newton's way of describing this worked well for centuries. Every object pulls on every other object, and the strength of that pull depends on their masses and how far apart they are. In that picture, gravity is a kind of invisible force stretching across empty space, tugging on planets, apples, and stars. Then, in the early 20th century, Einstein offered a different way of looking at it. In his General Theory of Relativity, published in 1915, gravity isn't a force in the usual sense. Instead, mass and energy bend the fabric of space and time themselves. You can imagine space-time, just for a moment, like an elastic sheet. A heavy object placed on the sheet makes a depression. Other objects roll along the surface and naturally follow curved paths because the sheet itself is curved. That's a rough picture, but it captures the main idea. Mass tells space-time how to curve, and curved space-time tells matter how to move. Shortly after Einstein wrote down his equations, a physicist named Carl Schwarzschild worked out a specific solution: what space-time would look like around a perfectly spherical, non-rotating mass. As he followed those equations to their logical conclusion, he realized that if enough mass were packed into a small enough region, the curvature would become so extreme that there would be a radius where light itself could no longer climb back out. Not because something was physically blocking it, but because every possible path through space-time led inward. If even massless light could not escape, nothing else could either. That critical radius is what we now call the Schwarzschild radius, and the invisible surface at that distance from the center is the event horizon. When you look at a picture of a black hole, you are not seeing the singularity. You're not even seeing the event horizon directly. You are seeing a darker patch where light paths have been bent and swallowed, surrounded by the bright matter still safely outside, swirling and heating as it orbits. The event horizon marks the line between regions where escape is still possible and regions where every path moves inward. From the outside, it's just empty space with an extraordinary geometry. But in terms of what information can reach us, it is a one-way boundary. Whatever crosses it on the way in does not send any more signals back out. Because space and time are bound together in Einstein's picture, anything that warps space also warps time. A massive object doesn't just bend the paths that light and matter follow. It also affects the rate at which time passes. Near any heavy mass, a planet, a star, a black hole clock's tick a little more slowly compared to clocks far away. The effect is tiny near Earth, larger near a neutron star, and dramatic near a black hole. Close to the event horizon, this stretching of time becomes extreme. To someone falling toward the black hole, their own time feels normal. Their heart still beats at the usual pace. Their thoughts arrive one after another as they always have. But to a distant observer watching from far away, things look very different. Light from the falling object has to climb out of a deeper and deeper gravitational well, losing energy as it goes. The signals arrive more and more slowly, redder and fainter each time. From that outside perspective, the infalling matter appears to slow down as it approaches the horizon. It seems to hover just above the boundary, moving more and more sluggishly, never quite crossing. Meanwhile, the light from it grows dimmer, stretched to longer wavelengths until it fades away entirely. There is no sudden, satisfying moment where you watch it snap out of existence. Instead, the image simply thins and disappears, as if the object has been gently erased. Inside the horizon, our descriptions become hazy. The equations that describe space-time suggest that all paths move inward, that the singularity lies in the future of anything that has crossed the boundary. But the way we talk about time and distance in that region no longer matches our usual experience. Some physicists say that, in a certain sense, time slows to a stop at the event horizon when viewed from far away. Others point out that for someone falling in, nothing special happens at that exact radius, at least locally. Both statements are true within their own frames. It's one of those places where language strains under the weight of reality, and we have to hold several perspectives at once. When these ideas were first proposed, they sounded almost too strange to be real. For decades, black holes existed mainly in the world of theory, solutions to equations, curiosities on chalkboards. Many astronomers and physicists wondered whether anything in the actual universe would truly collapse so far, or whether some overlooked effect would stop stars from crossing that last threshold. Then, gradually, observations began to catch up with theory. In the 1,960 seconds, new instruments sensitive to X-rays were launched into space. Unlike visible light, X-rays are mostly blocked by Earth's atmosphere, so they had remained hidden from view until we could put detectors above the air. Once we did, the sky lit up in new ways. Among the sources discovered was a particularly bright emitter in the constellation Cygnus, the Swan, an object that seemed to be pouring out an unusually large amount of X-ray radiation. Strangely, when astronomers pointed ordinary telescopes at that same region of sky, they didn't see a matching bright star that could easily explain such powerful X-ray emission. The source was there in X-rays, but in visible light, it was faint and confusing. They named it Cygnus X1, the first strong X-ray object catalogued in that constellation. Over the next few years, as instruments improved, astronomers studied Cygnus X1 more carefully. They found that there was, in fact, a massive star there, and that this star was wobbling ever so slightly, as if it were orbiting an unseen partner. By carefully measuring the motion of the visible star, how its light shifted as it moved toward and away from us, they could estimate the mass of the invisible companion. The numbers they found were striking. Whatever was tugging on the star appeared to be about 15 times as massive as our Sunday. That was too heavy to be a white dwarf, and too heavy even to be a neutron star, which are limited to around 2 or perhaps 3 solar masses before collapsing further. If the unseen object was not a normal star, and not any kind of stellar remnant we already knew how to describe, what was left? The simplest, if strangest, answer was that it was a black hole. Cygnus X1 became one of the first strong candidates for a stellar mass black hole in our galaxy, a place where theory seemed to have found a home in reality. Since then, many more such systems have been found. Bright X-ray sources, where gas from a companion star spirals into an unseen, compact object. We've also seen the signatures of enormous black holes in the centers of galaxies, monsters, millions or billions of times more massive than the Sun, whose gravity directs the dance of stars around them. In some cases, matter falling toward these central black holes forms immense, hot disks. As the gas circles inward, it rubs against itself, slows down, heats up, and radiates across the spectrum, from radio waves to X-rays and beyond. If there is enough matter falling in, these accretion disks can outshine the entire rest of their host galaxies, becoming quasars and active galactic nuclei. Even closer to home, in our own Milky Way, careful measurements have shown stars whipping around an invisible center near Sagittarius, moving so fast and so close that only a supermassive black hole can explain their orbits. In recent years, humanity has even managed to create images not of the black holes themselves, but of their immediate surroundings. By combining data from radio telescopes across the globe, astronomers have produced pictures showing a lopsided ring of light with a dark patch in the center. That dark patch is the shadow cast by the event horizon on the glowing material behind and around it. It is indirect, a silhouette rather than a portrait, but it is still a remarkable confirmation that something very much like the black holes of our equations really does exist. Through all of this, one detail remains the same. Black holes do not shine by themselves. They do not emit visible light or X-rays from within the event horizon. The radiation we detect comes from the matter still outside, from the accretion disks and jets formed as gas and dust spiral in and heat up to millions of degrees. Without that infalling material, a black hole is nearly impossible to find. A black hole drifting through mostly empty space, with nothing nearby to swallow, would be almost perfectly dark. We would only know it was there if we saw its gravitational pull bending the paths of stars or distorting the light of more distant objects. Even now, exploring black holes is a young and changing field. We've gone from doubting their existence to cataloging many examples, from equations on paper to crisp images of glowing rings. And yet, there is still so much we do not know. What truly happens at the singularity? If such a thing exists in the way we currently imagine it, how exactly does quantum physics, the world of the very small, blend with gravity, the shaper of the very large, inside and around these objects? Those questions are still open, still waiting in the shadows. You might find yourself wondering whether a black hole, once formed, lasts forever. If it keeps gathering matter and light, does it simply grow and grow until there is nothing left nearby to consume, a dark seed at the end of every story? At first glance, it can seem that way, an object that only gains and never gives back. Some ideas in modern physics suggest that black holes may, in the deepest sense, slowly lose energy too, leaking it away in ways that are incredibly slow and subtle on human timescales. But those possibilities unfold over periods so long that they are almost impossible to grasp, far longer than the age of the universe as we now know it. For tonight, it may be enough just to hold this quieter picture. Somewhere in the distance, there are places where matter has fallen so far that light cannot return. Around those places, gas glows and swirls, stars orbit in tight curves, and time itself moves to a different rhythm. The images we see are not of the darkness itself, but of how everything near that darkness is changed. And while the details are rich and complicated, the feeling they leave behind can be simple, a sense that the universe still holds regions where our understanding thins, where the laws we know bend into shapes we are only beginning to trace. There is a quiet twist in the story of black holes, one that arrived in 1974, when physicist Stephen Hawking suggested that, in a very deep and subtle way, black holes are not completely one way after all. In a paper with the almost shocking title Black Hole Explosions, he proposed that energy and therefore mass could slowly leak away from a black hole over time. It wasn't a dramatic explosion in the usual sense, but a delicate kind of fading. To understand why he thought this might be true, we have to step into a very strange corner of physics, one that looks not at stars or galaxies, but at the smallest, quietest parts of reality. That corner is quantum mechanics, and the first step along that path begins with a question that sounds simple, but isn't. What is nothing? You can try to picture an empty patch of space. Imagine a region where there are no stars, no planets, no drifting grains of dust. Imagine there is no faint gas, no wandering comet, not even a stray photon of light passing through. As far as you can tell, there is simply nothing there at all. A pure, perfect vacuum. But even in that imagined emptiness, something subtle still exists. We can tell, in part, because light can move through it. When we talk about light in everyday language, we might call it rays or beams. In physics, we also describe it as an electromagnetic wave, a pattern of electric and magnetic fields that perpetually generate and sustain each other as they move. A wave, though, is always something happening to something. In the ocean, a wave is not a separate object riding on top of the water. It is the water itself, moving up and down, passing energy along. A floating leaf rises and falls, but doesn't travel far. The energy goes on, carried by the motion of many tiny pushes, all the way to the shore. Sound behaves similarly in air. The air itself does not flow in a solid block from the person speaking to your ear. Instead, each tiny parcel of air vibrates a little bit, bumping the next, passing along a pattern of compression and rarefaction. Your ear feels those changes in pressure, and your brain weaves them into voices, music, and the quiet hum of the world. So, in both of those familiar cases, there is a medium, water for ocean waves, air for sound. But in the vacuum of space, when a photon of light crosses the emptiness between stars, there is no water and no air. The light still behaves like a wave. It still carries oscillating electric and magnetic fields. If you think of it for too long, a small question begins to form. If light is a wave, what is doing the waving when there is nothing there? That question hints at something deeper than simple emptiness. Even the most perfect vacuum we can imagine is not truly nothing in the way our minds first picture it. There is, at a fundamental level, a kind of underlying fabric present everywhere, a background that can still ripple, shift, and store energy. In the language of quantum physics, that underlying something is described as a set of quantum fields. You can think of a quantum field, very loosely, as an invisible sheet that fills all of space. Each kind of particle we know corresponds to a field, an electron field, a photon field, and so on. Even when there are no actual particles flying around, no little bits you could count, the fields themselves are still there, spread out and gently humming in their lowest energy state. They cannot be turned off or removed. They are the stage on which everything happens. Unlike a quiet sheet of water, though, quantum fields are never completely still. Because of the way quantum mechanics works, they are always trembling slightly, fluctuating in ways that are small but real. These fluctuations mean that empty space is more like a restless calm, a place where energy and disturbance never quite settle to absolute zero. There are virtual particles, briefly appearing and disappearing, tiny excitations flickering in and out of existence before they can be directly observed. This picture of space as a sea of ever-present quantum fields is not easy to hold all at once, especially when you're tired and drifting. You don't need to track all the details. It's enough to have a soft sense that even in the darkest, most silent regions of the universe, there is still a kind of hidden activity, a faint, ceaseless quiver in the fabric of reality. Near a black hole, those quantum fields meet extreme gravity. Space-time is curved so sharply that the usual notions of inside and outside, of here and there, are bent almost beyond recognition. Hawking's insight was to ask what happens to these restless quantum fields right at the edge of the event horizon, where the pull of the black hole is strongest, but still not quite absolute. In very simple terms, his calculations suggested that the interplay between quantum fluctuations and space-time curvature near the horizon could lead to radiation being emitted particles, gently escaping to infinity while their partners fall inward. To someone far away, it would look as if the black hole itself were glowing very faintly, losing a tiny amount of mass over vast stretches of time. This slow outflow of energy is what we now call Hawking radiation. The full story of how that works involves ideas that braid together general relativity and quantum theory in ways that are subtle and mathematically intricate. You don't need to carry all of that with you tonight. You can let most of it blur at the edges. The key feeling is this: even black holes, once thought to be perfect one-way traps, might not be entirely closed. In the relentless quiet near their horizons, where quantum fields and gravity meet, there may be a slow leak, a shimmer of energy that, over ages beyond counting, lets them fade. So from the hearts of stars to the stretched fabric of emptiness, from collapse to a whisper of evaporation, the story of black holes is bound up with how we think about nothing and something, about space that looks empty and space that is secretly alive with structure. If you let your thoughts float away from black holes for a moment and back out into the wider sky, another kind of eruption waits there, one that is much kinder to us and far easier to see. It doesn't twist space-time into knots, and it doesn't hide behind an event horizon. It simply flares, fades, and then, in a remarkable act of repetition, flares again. Have you ever wished you could watch a star's outburst with your own eyes, not through a telescope in a distant observatory, but just by stepping outside and looking up? Not a distant supernova in some faraway galaxy, but something closer and more personal. A star in our own sky that changes so dramatically you can notice it yourself? There is such a star. Astronomers sometimes call it the Blaze Star. By its more formal name, it is a binary system known as T Coronae Borealis, tucked away in a small, graceful constellation in the northern sky, called Corona Borealis, the Northern Crown. Most nights, it is modest and unassuming, too faint for casual eyes to pick out from the background. But every so often, it erupts in a way that transforms it into something striking, a recurring nova. The first of these dramatic outbursts to be well recorded took place in the spring of 1866. On a partly cloudy night in Western Ireland, not long before midnight, An amateur astronomer named John Birmingham was walking home in the dark. Like many who fall in love with the sky, he had the habit of glancing upward as he walked, checking on familiar patterns as if saying goodnight to old friends. As his gaze wandered toward the northern crown, he stopped. There, in a pattern of stars he knew well, was something that had not been there before. A new, bright point of light. It shone clearly enough to be noticed by eye alone. A sudden arrival in a slow and ancient design. Birmingham had caught sight of T Coronae Borealis in outburst, the blaze star flaring into view. A nova like this is not a star being born or a star dying, but a kind of repeated hiccup in the life of a binary system. One of the stars is a white dwarf, an extremely dense, compact remnant, no bigger than a planet but nearly as massive as the Sunday. The other is a more ordinary companion. Over time, gas from the companion star drifts toward the white dwarf, forming a thin layer on its surface. As that layer grows thicker and heavier, pressure and temperature at its base climb until, suddenly, nuclear fusion ignites in a flash. For a brief period, the surface of the white dwarf erupts, blasting energy outward and throwing some of the accumulated gas back into space. To us, far away on Earth, the system brightens dramatically. A star that was almost invisible becomes easy to pick out with the naked eye. A new star in a constellation that had, until then, seemed unchanging. Unlike a supernova, which is usually a one-time event that destroys the star, a nova of this kind can happen again and again. Once the eruption has passed and the system settles, gas begins to accrete once more. Slowly, quietly, the white dwarf gathers a new shell of material from its companion. When enough has built up, another runaway flash happens, another brief blaze, another chance for anyone watching at the right time to notice that something in the sky has changed. Because these outbursts are separated by decades, a recurring nova like T Coronae Borealis is, in a sense, a once-in-a-lifetime experience. John Birmingham stood under the Irish sky in 1866 and saw a point of light appear where none had been. Generations later, other observers have had their own moments of surprise and wonder as the blaze star woke again. In the years around 2024, astronomers expected yet another eruption, and people all over the world prepared to step outside on clear nights, to lift their eyes toward the northern crown and share that same simple, quiet astonishment. There's something gentle about that thought. Most of the time, the universe changes on scales too large and too slow for us to notice. Stars evolve over millions of years. Galaxies drift and collide over billions. Black holes grow and fade on timescales that make human history feel like the blink of an eye. But every now and then, a star in our own sky brightens for just long enough that a single person, walking home late or leaning on a windowsill, can witness it. Whether you are thinking about quantum fields trembling in the emptiness near a black hole, or a white dwarf drawing in gas from its companion until it flares, the same quiet truth runs underneath. The universe is never truly still. Even in the dark, even in the silence, there are processes unfolding, energies balancing and tipping, stories moving forward. And you, lying here, listening and breathing, are part of that same universe, a small, calm presence in a vast, restless sea, able to look up and notice when, once in a long while, a familiar patch of stars gains a new point of light. The name Blaze Star sounds like it belongs to a single, fiery sun. But the truth is a little more intricate and a lot more beautiful. What we call the blaze star is actually a pair of stars, a binary system, two suns locked in a long, slow orbit around a shared center of gravity. They are partners, circling each other in a quiet, gravitational dance. And it's the relationship between these two, their stages of life, and the way they trade matter back and forth, that makes the system flare into a nova roughly every 80 years or so. This idea of paired stars isn't unusual at all. In fact, astronomers estimate that perhaps half of the stars you see when you look up at the night sky aren't solitary like our sun, but members of multiple systems, pairs, trios, sometimes even more. Some glide around each other in wide, lazy loops. Others orbit in tight embraces, so close that their outer layers touch or even merge. The blaze star belongs to this crowded, social universe. It is not alone. Both stars in this system started life as average-sized suns, not so different in mass from our own. But time has carried them along different paths, and now they stand at very different points in their stellar journeys. To understand where they are, it helps to think for a moment about the life story of a star like our Sun, a small to mid-sized star. Right now, the Sun is about 4.6 billion years old, well into what astronomers would call its middle age. In this long, stable phase, it quietly fuses hydrogen into helium in its core, shining steadily, warming the planets that circle it. But this calm doesn't last forever. In roughly 5 billion years, the Sun's core will have used up most of its hydrogen fuel. Fusion will slow and shift to new layers, and the balance between pressure and gravity will begin to change. As that happens, the Sun will swell. Its outer layers will puff outward and cool, turning it into a red giant larger, cooler at the surface, but still burning fiercely within. In that swollen phase, it may grow so large that it engulfs Mercury, Venus, and perhaps even Earth, if our planet is still there to be engulfed. The exact details are still being studied, but the broad outline is clear. The Sun will become enormous, fragile, and unstable. After some time in this expanded state, the Sun will shed its outer layers into space, casting off shells of glowing gas. Those gases will drift outward and thin into a soft, colorful cloud known as a planetary nebula, while the core that remains behind contracts into something much smaller and denser, a white dwarf. This white dwarf is the bare heart of the star, a hot, compact remnant roughly the size of Earth but with about half the Sun's mass. It will no longer fuse elements in its core. Instead, it will simply glow with leftover heat, slowly cooling over billions and trillions of years, its light fading toward darkness. White dwarfs are sometimes called dead stars, though that word can sound harsher than they deserve. They are not dead so much as retired cores that have finished their long work of fusion and now spend ages gently cooling, like coals that no longer feed the fire but still hold a quiet warmth for a very long time. Both members of the blaze star system are on this general path, but they have moved along it faster than our Sunday. One of them has already reached the red giant stage, its outer layers swollen and delicate. The other has already passed through its own red giant phase and settled into life as a white dwarf. It is this contrast, one star puffed up and vulnerable, the other small, dense, and powerfully gravitational, that sets the stage for the recurring nova we can see from Earth. As the red giant expands, its outermost gas is no longer tightly bound. The star's surface grows cooler and more diffuse. Around it, the gravitational influence of the white dwarf becomes more important. There is a region, a kind of invisible boundary around each star in the pair, within which matter feels more strongly bound to that star than to its companion. As the red giant swells, parts of its atmosphere cross that subtle line and begin to feel the pull of the white dwarf more than the pull of their original home. Slowly, gently, hydrogen-rich gas from the red giant begins to drift toward the white dwarf. In some places, this transfer forms a thin stream or a faint disk spiraling down onto the dwarf's surface. You can picture it, if you like, as a very slow, very quiet, siphoning one star, donating its outer layers to another, bit by bit. The white dwarf, with its intense gravity, acts almost like a cosmic vacuum cleaner, gathering this borrowed material into a thin shell. At first, not much seems to happen. The newly arrived gas settles onto the dwarf's surface, spreading out and building up. Over time, though, as more and more hydrogen accumulates, the pressure at the base of this layer increases. The temperature rises. Deep within that thin shell, the conditions begin to resemble a miniature stellar core. The hydrogen is squeezed and heated, trapped against a surface that is already incredibly dense. There comes a point when the pressure and temperature cross a critical threshold. Suddenly, hydrogen fusion ignites in a runaway flash across the surface. Unlike the steady, self-regulating burning in a normal star's core, this process on the white dwarf is unstable. Once it starts, it races through the accumulated layer rapidly. In a brief burst, enormous amounts of energy are released. The shell of gas is blasted outward into space, thrown off in an expanding cloud. From the white dwarf's point of view, it is like a sharp exhale after a long inhalation. From ours, over 3,000 light-years away, it appears as a dramatic brightening. The blaze star, usually too faint to distinguish from its neighbors without careful charts, suddenly surges in brightness, becoming up to about 1,500 times more luminous than usual. For a few days or weeks, it can be seen with the naked eye, a new star, shining where the constellation once looked quiet. This kind of event is called a classical nova. It is a powerful explosion, but not a fatal one. The white dwarf survives. It loses the shell of hydrogen it had collected, but its core remains intact. After the eruption, the system gradually settles back into its quieter state. The red giant continues to overflow a little. The white dwarf begins collecting again. Over decades, the process repeats. Accumulation, pressure, ignition, release. In the case of the blaze star, this cycle takes on the order of 80 years or so. Each lifetime, if you know where to look and you happen to be alive at the right time, you may see it flare once. This is very different from the more famous and more violent supernovae. In a supernova of the kind that destroys a solitary star, the explosion is not just a surface flash. It involves the collapse of the star's core and the complete disruption of its outer layers. To reach that kind of end, a star must start life far more massive than the Sun, typically with at least 8 times the Sun's mass, and often much more. The stars in the blaze star system are not that heavy. Their nova is a surface event, a temporary reversible burst. A supernova is a fundamental transition, one that leaves behind either a neutron star or a black hole and unbinds the star forever. The difference in brightness reflects this difference in scale. A classical nova like the blaze star may become thousands of times brighter than its usual self, impressive and noticeable across thousands of light years. A core collapse supernova can be millions or even billions of times brighter, briefly outshining its entire host galaxy. Compared to that, a nova is a gentle event, a firework against a background of deep night, Instead of a flash so intense it rivals the brightness of everything around it. The closest star we know of that is on a path towards such a dramatic core collapse supernova, at least in cosmic terms, is Betelgeuse, the red supergiant in Orion's shoulder. You might remember its soft, reddish glow from earlier. One of the 10 brightest stars in the night sky, despite being roughly 600 to 700 light-years away. Betelgeuse is extremely massive, swollen, and unstable. Its core is believed to be working through the last complex stages of fusion, building up toward the iron limit that precedes collapse. When astronomers say Betelgeuse might explode in the near future, they mean it in the language of galaxies and stars. That could still mean tens of thousands of years from now. On human timescales, that is unimaginably long. There is essentially no chance of it happening in our lifetimes. There is almost no chance of it happening within the lifetime of our distant descendants. But in the history of the star itself, which has already burned for millions of years, that remaining time is a closing chapter. If, one night in some distant age, Betelgeuse does finally go supernova, the view from Earth would be extraordinary. After the initial collapse and explosion, the star would brighten until it rivaled the full moon. For a while, it would be visible even in the daytime sky, a new, brilliant point of light glowing near the familiar pattern of Orion. Shadows might be cast by a second moon of starlight. People everywhere would step outside, look up, and see the silent bloom of a star dying far away. Events like that are rare. In all of recorded human history, there have only been a handful of supernovae bright enough to be seen with the naked eye and carefully documented. The oldest well-known record, now associated with what we call SN 185, comes from Chinese astronomers observing the sky in the year 185 AD. They described a guest star that appeared where none had been before, stayed visible for about 8 months, and then slowly faded. Today, modern astronomers have found the remains of that explosion, a shell of glowing gas expanding into space, confirming that those ancient observers were witnessing a true supernova. Another famous example came in 1604, when the German astronomer Johannes Kepler meticulously observed a new star appearing in the constellation Ophiuchus. It became so bright that people could see it during the day, a piercing point in the blue sky. Kepler charted its changes night after night, not knowing that centuries later, we would still be studying the remnants of that same explosion, now a faint, expanding nebula. These recorded supernovae are like bookmarks in the history of the night sky, rare moments when the slow dance of stars becomes fast enough for human eyes to follow. Between them, there have been other bright novae as well, classical novae like the Blaze star flaring briefly into view before retreating again. Each one is a reminder that the heavens, which can look so steady and fixed, are actually full of things that change, flare, and fade. So when you think of the Blaze star and its recurring nova, you can place it gently on this spectrum of stellar fireworks. It is not as final or as overwhelming as a supernova, but it is intimate and reachable. It is a nearby system, only a few thousand light-years away, whose changes are bright enough to touch your own unaided eyes. It is the story of 2 average stars at advanced ages, one swelling, one compact, sharing material and occasionally letting that shared weight ignite into a brief, luminous sigh. Somewhere, right now, the white dwarf in that system is collecting a new layer of hydrogen from its red giant companion. The pressure is slowly building again, atom by atom, in absolute silence. On Earth, clocks tick and days pass. People live and forget. And in time, perhaps decades from now, perhaps close to a date, someone has predicted that quiet buildup will cross its threshold, and the blaze star will once more brighten in our sky. If you happen to be there to see it, all you will need to do is step outside, tilt your head back, and notice that in one small crown of stars, something old has flared new again. What the blaze star is expected to offer us is not just a pleasant little flicker, but one of the brightest classical novae of this entire century. For something that lasts only days to maybe a week, in its full glory, it carries a surprising weight of rarity. Events like this do not line up very often with a brightness high enough and a position convenient enough for almost anyone to step outside and see them with their own eyes. Classical novae themselves are not quite as rare as supernovae. Somewhere in our galaxy, about once every year or two, a white dwarf in a binary system gathers enough material from its companion to ignite its surface and flare up. For a short while, a faint star becomes many times brighter than usual. But most of these flares remain subtle. They peak at magnitudes that are just beyond the reach of an untrained eye, or hidden by city lights, or tucked into parts of the sky where few people routinely look. The sky does change, but often so quietly that only those with telescopes and careful charts notice. The blaze star is different because, when it erupts, it is expected to cross an important threshold. It may become bright enough to be obvious even to someone who is simply outside at night, looking up without any special equipment. Among the classical novae of the last few decades, it could be one of the most striking, a rare moment when the universe chooses a brightness and a position that invites almost everyone to participate. Astronomers have a way of putting numbers to this kind of brightness, a system that can sound backward at first if you're not used to it. It's called apparent magnitude. The word apparent reminds us that this scale measures how bright something looks from Earth, not how much energy it truly emits in all directions. And the scale itself runs in a direction that can feel a little upside down. The smaller the number, the brighter the object. So, a star with magnitude 1 is brighter than a star with magnitude 2. A star with magnitude 0 is brighter still. Some objects are so bright that their magnitudes are negative. On a very dark, clear night, far from city lights, the human eye can usually reach down to about magnitude 6 or 6.5. Fainter than that, objects tend to disappear into the background. They may still be there, of course, sending their light toward us, but that light is too thinly spread for our eyes to catch. To put some familiar points on this scale, you can think of the Big Dipper, the 7 stars that many people learn to spot first in the northern sky. The brightest of those stars shines around magnitude 1.7, while the faintest sits near magnitude 4.8. All of them are comfortably visible from a reasonably dark place. The brightest star in the night sky, Sirius, in the constellation Canis Major, is far more intense at about magnitude 1.4. On cold winter nights, it can look almost like a shard of ice, crisp and vivid. The sun, dominating our daytime sky, has an apparent magnitude of around 26.5, a reminder of just how vast the range of brightness really is. The blaze star, in its usual state, sits quietly at about magnitude 10. That's far too dim for the unaided eye. Even in excellent conditions, you would need a telescope, or at least a good pair of binoculars and accurate charts to pick it out. To most people, most of the time, it effectively does not exist as a separate, noticeable point. It is there in the data, but not in the ordinary experience of looking up. During a nova outburst, however, everything changes. When the white dwarf's collected layer of hydrogen ignites and blows off, the system's brightness leaps upward. Historically, the blaze star has brightened to around magnitude 3 at its peak. That's bright enough to see without any optical help, as long as the sky is reasonably dark and you know where to look. For the next eruption, some estimates suggest it may reach magnitude 2 or even a little brighter. Magnitude 2 might not sound particularly impressive compared to a star like Sirius, but on the scale of naked eye astronomy, it is more than enough to stand out. The North Star, Polaris, which many people use for orientation, has a magnitude of about 1.97. If the blaze star reaches around magnitude 2, it will rival Polaris in brightness. Imagine glancing up at a familiar ring of stars and seeing a new point shining with almost the same insistence as the star that marks the direction of north. It would feel, for a brief time, as if the sky itself had gained a new landmark. The word nova comes from the Latin for new. Long before telescopes, when people saw a bright star appear suddenly in a part of the sky that had always seemed empty or modest, they naturally thought a new star had been born. To them, the heavens were steady and fixed. The occasional arrival of a bright point that was not there before must have felt like a message, a sign, or at least a deep mystery. Only later did astronomy reveal that these new stars were often old systems behaving briefly, dramatically differently eruptions, not births. Even in modern times, novae can surprise us. In 2013, for example, a nova in the constellation Centaurus brightened unexpectedly to become one of the brightest in more than a century, reaching a peak magnitude of around 3.3. Many people with clear southern skies could walk outside and see it, a temporary newcomer among the familiar patterns. It reminded astronomers that even though we know, in broad strokes, how novae work, the details of each event can still elude precise prediction. The blaze star itself last erupted in 1946. During that outburst, observers recorded it at about magnitude 3. At maximum, a clear, easily visible star for anyone who happened to be watching Corona Borealis at the right time. For most of the 20th century afterward, it returned to its quiet, hidden state, doing its work unseen. The red giant losing matter, the white dwarf accumulating it, pressure and temperature building slowly in the thin shell. Decades have passed, and with them, generations of people have lived under a sky that, to their eyes, did not contain the blaze star as anything special. When it flares again, whether you think of that flare in the context of a particular year or simply as the next step in its 80-year heartbeat, it is likely to be even brighter than in 1946. Predictions suggest a peak around magnitude 2, perhaps a little better. For a short while, this normally invisible system will stand shoulder to shoulder with some of the sky's more familiar lights. And then, as surely as it brightened, it will begin to fade. The show does not last long. A classical nova like the blaze star usually climbs to its maximum over a short period, days rather than weeks, then declines gradually. The time it spends bright enough to be obvious to the naked eye might be only a handful of days, or at most a week or two, before it sinks back below the human eye's limit and disappears again into the quiet. There is no precise clock we can set for that eruption. The timing depends on how fast material flows from the red giant, how it spreads and accumulates on the white dwarf, and exactly when the conditions in that thin shell cross the threshold for runaway fusion. Astronomers can estimate and narrow down the range based on past behavior and current observations, but the star picks its own moment. In a way, that uncertainty is part of the charm. There is something gentle about knowing that the universe will not perform on cue. You can't order a nova for a particular evening. You can only remain attentive, be willing to look up, and perhaps be rewarded. If you want to know where to look when that reward comes, you can trace your way to the blaze star, step by step. Choose a clear night, away from bright city lights if you can. Let your eyes adjust to the dark for a while, allowing the fainter stars to emerge from the gray. In the northern sky, the constellations Hercules and Boötes form two distinct patterns. Hercules as a somewhat skewed quadrilateral of stars with arms and legs suggested in faint lines. Boötes as a tall, kite-shaped figure crowned by the bright star Arcturus. Between these two lies a smaller, graceful pattern, Corona Borealis, the northern crown. It looks like a delicate semicircle of stars, an arc of tiny points curving across a small patch of sky. On a sufficiently dark night, the entire curve is visible, a little jeweled circlet hanging quietly between its larger neighbors. If you start at the side of the crown, closer to Boötes, and follow the arc of stars toward the side nearer Hercules, you can trace the semicircle from one end to the other. In its usual state, the blaze star sits just below the last star of the crown on the Hercules side, too faint to notice without a telescope. During a nova, that same spot will blossom with light. A stranger will have joined the curve, hovering just beneath it, changing the shape of a pattern that has, for all practical purposes, looked the same for your entire life. If you have access to a small telescope or a good pair of binoculars, you might try seeking out the blaze star's location even before it erupts. With charts or an app to guide you, you can become familiar with the small, faint points in that part of the sky, anchoring your memory of how the northern crown looks when everything is quiet. Then, when the nova happens, you will be able to feel the difference more intimately. You will remember a patch that once seemed empty, and you'll be able to say, with a kind of quiet conviction, that wasn't there before. For astronomers, these novae are not only beautiful, they are also generous. Each eruption offers a fresh chance to gather data, to measure exactly how the brightness rises and falls over time, to spread the light into a spectrum and see which elements are glowing, to estimate how fast the ejected shell is expanding. Taken together, such observations refine our models of how white dwarfs accrete matter, how thermonuclear runaways begin, and how mass is lost and shared in binary systems. They help us understand, in detail, how stars evolve in pairs, and how some white dwarfs may, given enough mass, eventually cross the line into a type of supernova of their own. But you don't need to follow the graphs or understand the equations to appreciate what the blaze star is offering. It is enough to know that somewhere, in a small constellation shaped like a crown, two stars are locked together in a relationship so intense that every few human generations, it spills over into a burst of light that reaches us across 3,000 years of distance. If you happen to live through one of those bursts, and you remember to step outside on a clear night and look up, you will be sharing that moment with countless other eyes, past and present. With observers in 1946 who watched the same spot brighten, with John Birmingham in the 19th century who stared in surprise at a different new star, with ancient sky watchers who did not know what a nova was, but recognized that their familiar patterns had been altered. Most nights, the stars seem eternal and unchanging, a fixed backdrop against which our brief lives unfold. Novae, like the blaze star, gently remind us that even the stars have their tempers and turning points, their quiet accumulations and sudden releases. They have lives that include not just slow, graceful aging, but also moments of dramatic transformation, like fireworks set off in the depths of space. Knowing that, you might feel a small shift in how you see the sky. It is not only a ceiling of lights, but a collection of ongoing stories. Somewhere above you, tonight, or some night to come, a white dwarf is pulling in gas grain by grain. A layer is thickening, pressure is building, and the future brightness of a new star is being prepared. When it finally arrives, and you tilt your head back to greet it, you may feel just a little more grateful to be here on this one small planet, at a time when you can witness such a fleeting, radiant pause in the slow breathing of the universe. If you let your mind wander back over everything we've passed through together, it begins to feel a little like walking a long, slow arc across the sky. We started with a single red point in Orion's shoulder, a star swollen and fragile, carrying in its heart the seeds of a future supernova. From there, we drifted through Hubble's portraits of distant nebulae and galaxies, pillars of dust where stars are born, filaments of gas where stars have died, broad spirals whose cores hide invisible weights. We paused beside black holes, where gravity folds space and time so deeply that even light loses the path home. And we listened to the whisper that they might, in the faintest way, glow and fade over ages through Hawking's quiet radiation. Then we turned back towards something closer and more personal, the Blaze Star, a small, recurring fire in the northern crown. Not an ending like a supernova, not an ultimate plunge into a black hole, but a repeating breath in the life of a binary pair, a red giant and a white dwarf, sharing matter, stacking up tension, and then, every few decades, releasing that tension in a brief, luminous outburst we can actually see, a reminder that some of the universe's stories are long and unreadable, and some are timed just right for human eyes. The thread tying all of these together is the simple fact that nothing in the cosmos is truly still. Stars are not fixed jewels. They are long processes, caught in a moment. A red supergiant is a star nearing its last lines. A white dwarf is a final ember, cooling slowly. A nova is a flash written on the surface of a worn-out core. A black hole is the memory of collapse turned into a shape in space-time. Even the deep emptiness between stars is stirred by quantum fields that never quite sleep. And yet, from where you lie or sit right now, the night can feel so calm. The stars seem to move only with the turning of the earth. The constellations return season after season, like old, familiar stories. It is easy, and maybe necessary, to let them feel permanent. Our lives are short compared to their cycles. Their changes are mostly too slow or too far away for us to watch unfold in real time. That's why events like the Blaze Star's nova matter in a quiet, human way. They compress a piece of stellar evolution into a timescale we can share. They take something that usually happens invisibly and tuck it into a few nights of brightness, a small gift in the long, patient work of the sky. Whether or not you ever catch one with your own eyes, knowing that they happen that right now, somewhere, pressure is building toward a brief flare is enough to soften the idea of a static universe into something more alive. If all of this feels too large to hold, you don't have to. You can let the technical names blur and the numbers fall away. What remains is a gentler picture, a universe that breathes in cycles of light and dark, of collapse and expansion, of gathering and release. Red supergiants swelling, white dwarfs cooling, black holes deepening, novae blinking on and off like slow, distant fireflies. Somewhere under all of that, there is you, on a small world wrapped in air, listening in the quiet hours while the sky turns overhead. You are not outside this story. You are a tiny part of it, made of the same heavy elements once forged in stars and thrown into space by ancient explosions. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it has passed through furnaces far older than Earth. So the next time you find yourself under a clear night, you might take a moment to look up a little longer. Maybe your eyes will find Orion, or the curl of the Northern Crown. Maybe you won't see anything unusual at all, just the usual points of light in their familiar places. That's all right. Knowing what is hidden behind that calm is its own kind of comfort. The universe will go on changing at its own unhurried pace. Stars will swell and fade. Black holes will continue to wait at the centers of galaxies. And once in a while, a quiet spot in the sky will brighten briefly and then sink back into darkness. Tonight, though, you are allowed simply to rest, to let the thought of those distant motions rock you a little, the way waves do against a shore you can't quite see. The stories written in starlight will still be there when you wake.